All right. So last time, what we did, we covered uh, how simple electronic systems try to move around charges to produce radiation. So what we did, we started an analysis with a very simple structure, or with a very simple charge particle, say one electron or one positive charge atom. And if we move that positive charged particle up or down, then this information propagates through free space, because there's a variation in electric field, and that variation in electric field propagates through free space at a speed of light. We looked at this very simple analysis and expanded it towards a sheet of charge. So if we have a sheet of charge and we move that sheet of charge from a particular point to another point at a velocity v, then there will be some variation in electric field, and because of that variation in electric field, there will be time varying magnetic flux density. The time varying magnetic flux density will then produce electric field, and so on. So there will be a little bit of variation in this, and that variation will propagate through free space. We also looked at some expressions, how we can mathematically describe this phenomena, and then we looked at this particular example in which we have sheet. If we move the sheet up and down and up and down, electric field will produce, magnetic flux density will produce, and according to Poynting's theorem that we have seen in the previous lectures, we can say that a Poynting vector E cross product H is the energy flow, and that energy flow will radiate. That energy flow will be towards this direction and towards that direction because of this moving of the sheet of charge. Okay. So now let's go back to our previous discussion, that how fast we can move this sheet up and down is a question. So let's forget about this physical phenomena. Let's jump back into engineering domain. If my finger is a charged particle, I can move this charged particle up and down so many times a second. So for example, I can achieve 10 hertz at maximum. But what if I want to produce a wave, a sinusoidal wave, that the frequency of which is higher than this 10 hertz? What I have to do? I have to go towards mechanical means. I need a mechanical motor that is kind of moving a thing up and down. But after some time, our mechanical structures will also have a limitation. There is simple motor can go to a specific RPM, and after that it will kind of burn out. So what we understood as humanity, that the electric field has more capacity. So what it means is that the alternating voltage source has a capacity. Alternating voltage source has a capacity of producing very, very, very high frequency signals. So high that we can actually feed some metal stripes, and in those metal stripes, if there are free current carrying charged particles called electrons, then we can move those electrons up and down, and because of this movement of electrons, we can produce something like this, that is a radiating field at a frequency f. Okay, so this is a very good kind of achievement that we have done so far, and we use these devices every now and then. So today we will move away from this theoretical realm and into practical antennas. Okay, so now let's consider we are engineers, and someone is telling us that build a simple antenna or build a simple device that can radiate at a given frequency f. What should be the easiest way of doing that? So we will start with very, very fundamental level understanding of this concept. So let me first go towards the philosophy of what we are trying to achieve. And once again, you're going to answer a few questions. Okay. How many of you have teeny tiny understanding of electromagnetic theory? You have a teeny tiny understanding of electromagnetic theory. Okay, then you are ready to answer a few questions. Perfect. Okay. Imagine I have a charge particle. Okay. Simple positive charge. Will there be electric field lines going out of this charge? Is this a reasonable explanation? Yeah. They will go towards infinity. Okay. If I move this charge particle from here to here, there will be variation in this electric field, right? This variation will propagate through free space as this vector, because it should ideally be here, but it's here now. So there is a kink. Kink is moving away from this particular charge particle. Make sense? Is there any magnetic field involved here? In this phenomena, is there any magnetic field happening? Okay. What's this? What is this? Magnet. Does magnet has electric field or magnetic field? Okay. Let's call this magnetic field. Okay. H. This is E. Okay. Consider or imagine a free space environment where there is nothing, only vacuum, and there's a simple magnet sitting there, right? There will be magnetic field, right? Will there be any electric field? Just one magnet. Will there be any electric field? No? No? If I am here, there's electric field. Will there be magnetic field here? No. Will there be electric field here? No. But what if I move this charge from here to here? Will there be any magnetic field? Why? So rate of change of charge is current, right? So if a charge is moving, there's a teeny tiny current happening here, right? That teeny tiny current, according to which law? Which law? Ampere's Maxwell's law. Faraday's law is the other way around. So Faraday's law is there. Ampere's Maxwell's law is here. Okay. There will be teeny tiny current, and that teeny tiny current will produce magnetic flux density, right? So if we do this, then there will be a magnetic flux density. Okay. And with this E, there will also be an H. And what is Poynting theorem? What is energy Poynting energy flow? E cross product H, right? So if I do this, there will be teeny tiny current. That teeny tiny current will produce magnetic flux density or magnetic field. They are interchangeable, and there will be an energy flow moving away from here. Make sense? So what are we saying here is in an ideal world, there will be electric field if there are charged particles. In an ideal world, there's magnetic flux density or magnetic field if there's only magnetic particles. Okay. If they both are moving, they are producing instantaneous current. That current will translate into one another. That can produce electric field because of magnetic flux density, or that can produce magnetic flux density because of electric field. Make sense? Okay. Now, you are an engineer. If I want to practically do this, can you do it? I want a bunch of engineers. I am just giving them a task. Okay, take a charged particle, move it from A to B. Can you do it? How? That's a good answer. Yes, but how? Yeah. Put another charged particle where? Okay, so a positive charge here will kind of repel this one, and it will put, okay. So to make sure that this positive charge is coming here, what should I need to do? Okay, let me help you. Can I do it using a simple battery? What a battery does? From positive terminal, it pushes away some of the charges. From negative terminal, it pulls some of the charges. So there's a movement of charges happening, right? So a simple battery, if not connected to a load, will do nothing, right? But if it is connected to a load, then what it will do? It will do exactly what you've said. Push a bunch of charges from here so that there is net negative charge here, and pull some of the electrons from here so there is a net positive charge here. Okay, so here's the thing. A small electron from here will move this towards this direction or the other direction. Okay, so just for the concept. Okay, so we have done that. Perfect. What have we produced if we do this phenomena? Electric field, and that electric field has produced a small current. Small current produce magnetic field, energy flow through outer space. Perfect. But at what frequency exactly? This will only happen once if this battery is connected, because battery is DC, right? What if I want to do the same thing at a given frequency? What I need to do? Connect to AC. Okay, let's remove this connection from here, connect it to AC. If this frequency is, say, 100 hertz, what will happen here? The charges will move up and down and up and down and up and down, and then there will be 100 hertz signal. Of course, it will not be efficient because just a wire. But if you want to make it efficient, then there are some other engineering things coming into play. Okay, but do you understand the concept? So now that's basically a merger of the theoretical world and the practical world. In theoretical world, we knew this will happen, but practically how to do it is a question mark. And we want to solve that question mark. This question mark has already been solved, so we are just going to see how exactly. Okay. So a simplest form of antennas is basically this phenomena happening at a small stripe level. So what happen is we will have a small positive charge, and with a small positive charge, a negative charge. And we kind of flip this positive and negative charge like this at a given frequency f. And because of this given frequency f, there will be a radiation happening. Okay, this is the simplest form. Some people call it Hertzian dipole. I call it simple dipole. Okay. So if a simple charge particles plus minus is situated in vacuum, then practically it's not possible. So we have to give it something to stay on. That thing is simple metal. Simple metal. Okay, simple metal have free charge particles. We can flip those charge particles up and down. So imagine I have a very small metal strip that has positive and negative charge on two sides. This simple arrangement is called dipole. Dipole. Because it has di mean two, pole means polarities. So positive and negative. Let's make them different. Okay, positive and negative. This is called simple dipole. Okay. So if I have a simple dipole and it is moving, then this dipole, this phenomena will produce a current, small current I. This small variation will have a length L. So I can call it as IDL. Small variation of length L and a current I. And this current is going to produce what I have seen here. Okay. So if I have a simple dipole, then I can write an equation dq over dt is equal to I. You have already seen this equation before. Cos omega t. If it was a DC thing, then dq over dt is equal to I is enough. But since we want to produce current at a given frequency, we need to introduce a sinusoidal function as well. And that sinusoidal function is simple cos omega t. Omega is, what is omega? Omega is equal to 2 pi f. Omega is equal to 2 pi f. Right? F is, what is F? Frequency. Frequency at which I want to create a signal. What is T? T is time. Okay. So this equation has everything I need. It has current. It has cos, sinusoidal function. Omega is 2 pi f. Frequency. T is moving forward. So what it is telling me is rate of change at which this charge is moving will produce a current, and I can manifest that current in terms of a sinusoidal function, and sinusoidal function having a frequency f. Okay. It's simple to understand, but let's move one step more towards practical side. So this simple dipole that I have drawn there, a simple plus and minus at a very small distance dl, is not practically possible because where am I going to put it? Okay, so what I need practically is bunch of these small little things. Okay, and bunch of these small little things will give me something like a simple positive, a negative. Okay, small dipole, length dl, very small, basically approaching to zero, length approaching to zero, and it has current I. Okay, if I put another similar dipole here with a little bit lower intensity, so let me make this box based on this intensity, a smaller box. So smaller box means less coulombs, bigger box means more coulombs. And another one, plus, minus. So this is dl approaching to zero. This is dl approaching to zero. This is another I. This is another I. I3, I2, I1. Okay. Does it make sense? If I do this for some time, then there's a possibility that I will be able to produce a simple structure that has varying charge on it. So what this means is more charge variation, so more positive. What this means is less charge variation, less positive. So I can produce a simple stripe that has charge like this. Okay. So using simple dipoles, I can produce a simple stripe, and this thing is practically possible. We have these things actually lying around everywhere around us. A simple metal strip that has different charge density along its surface. And if this charge density is changing with respect to time, then this is an antenna. Okay, make sense? Okay, so there is a bit of maths involved in our understanding as well. Let's go to that maths. So we can build something like this. And if we have something like this, then we can have current I flowing through this dipole structure. And this dipole structure, if placed at the center of Cartesian coordinate system, then we have very, very precise equations that can actually explain how much electric field and magnetic flux density we are going to get in free space. Okay. So on the right side, you have a diagram in which you have this IDL cos omega t, a simple dipole at the center of Cartesian coordinate system. We have phi here, theta here. It's a simple spherical coordinate system. And at this point, at a distance r, we have h phi e theta, and h phi e theta are perpendicular to each other, and their cross product will produce magnetic my pointing vector that is going in the perpendicular direction, that is er. Okay, so this is a simple, you can say, representation of a fictitious dipole antenna. This simple arrangement is also called Hertzian dipole. Hertzian dipole. It's a fictitious dipole. It doesn't exist in nature, but we can build a simple half-wavelength dipole using similar principle. Of course, Hertzian dipole has some kind of maths associated with it, which doesn't apply to real world. But when we talk about half-wavelength dipole, then that maths will change a bit, but it will still be pretty accurate based on this dipole antenna explanation. Okay. So oscillating electric dipole will produce our E theta. E theta is electric field along theta axis, and ER, that is electric field at a distance r from the center. And these equations will give us something that are given here. So proof of these equations is not in your course, but you should know each and everything that is in this equation. Let's go towards that. Let's go and see if we know everything in this equation or not. Okay, first equation is E theta is equal to something is equal to something else. Let's look at that something else. What is I? I, current. What is DL? A small length of dipole. What is DL approaching to? 0. Why? Very, very small. Yes, it's approaching to 0 because it's very small. It's fictitious. Sine theta. You know theta? What is theta? In spherical coordinate system. Have you seen theta before? Theta is like this angle. Okay. What is sine omega? Omega is 2 pi f. T is time. Okay. So we have theta. It means space coordinate. We have time, its time coordinate. So this equation is valid in space-time, which we are in. Okay, so it makes sense. 4 pi epsilon. What is epsilon? Epsilon? Permittivity. If it's epsilon naught, then it's permittivity of free space. But it's epsilon, it means just permittivity. Okay. Omega, you already know. What is R? R is the distance of observation from the origin, right? R is distance of observation from origin. So this equation have everything that we already know, we are comfortable with. Okay, I'm not going to ask you to prove this equation because it's out of your scope, but this equation is making sense. Other equation is ER. It has all similar things, but I think there's 2IDL something like that and cos function. Yes, 2I and cos function. Two things are different. Okay. So what we have seen here is if we have similar arrangement, like this one, that is a simple dipole plus minus having a length dl approaching to 0, that will produce small current I that is placed in a spherical coordinate system where this is theta, this is phi. Then at any given point in free space, at any given point at a distance r from this, we have accurate equation that can demonstrate what is E theta. We have accurate equation that can define what is ER. Okay, and we have similar equations for H and H for the other perpendicular coordinate as well. Very accurate equations. Okay, so what it means is if we build something like this, then we can expand our analysis by placing simple fictitious dipoles on top of each other. So what I mean by that is if we have one fictitious dipole here, we know what is electric field here. Okay, so if we move that at a distance, very small distance, and another small distance, and add it together, then according to Maxwell's equations, we can actually add all the electric fields because of each individual small dipole. And if we add all these, we will have an accurate electric field here. Okay, so this is basically what we do in many computer aided systems that basically build antennas. They have very accurate equations around E theta and E phi for a fictitious element. So what they do, they build a huge structure. They divide that structure into small little chunks, and they calculate using like high intensity computers. We have very good computing facilities here in Belfast for doing these kind of jobs for us. So this is pretty much possible. So if we look at the total pointing vector in theta, that is basically cross product, but this cross product has been done and we are getting a final resultant negative ERH phi. Then I will have this long equation, and trust me, you know majority of the things in this equation. What we have seen before is basically there. There's an additional thing that is c. C is speed of light. Okay, so proof of this equation is out of scope. So if I am going to ask you, I will give you this equation and I will say, explain this equation. And then you will be like, okay, because everything that you have already studied is there. Okay, so similarly with PR, we have PR average. Average is basically, there is a bit of derivation involved here, which I'm not going to ask you about. So after that derivation, we can actually state exactly how much power we are getting at a point P in space when we have a fictitious dipole at the center of origin, and that is given in this equation, and it has this eta And eta is another thing that you already know about. So anyone who can tell me about eta is a champion. What is eta? What's eta? Something of free space. Eta has a value. What's eta? We have covered this. You all have your notes. What is eta? Let me put you in awkward situation. What is eta? What is eta? You have it in your notes. Not here. Space. Permittivity is epsilon. Maybe. What is eta? Impedance of free space impedance. What's its value? 377 ohms. It's not that difficult, guys. Please wake up. So eta is free space impedance. So what this equation is telling us is the power that I'm going to receive at a given point if I have a fictitious dipole at the origin depends on free space impedance as well. So here, impedance, free space impedance is an important factor that will translate into power. And this eta with this C and R, they all are extremely, extremely important for us. So if you are an engineer and I ask you to build a simple dipole antenna, then you need to be considerate about all these factors. You need to be considerate about R. R is the distance from origin to you. R, eta, it is the wave will propagate through free space. So impedance is what you need to consider. Sine theta, Cartesian coordinate system, I, what kind of current you are going to get. And 2 pi r, r is the distance, and c is speed of light. Okay, so eta can be calculated using epsilon and mu as well. So eta has a relationship with epsilon and mu. So this is going to give you P, that is power in watts per meter square. Okay, so very, very practical thing, very, very practical thing. If we know that there is a fictitious dipole here, and if I am interested in how much power I will get in this aperture area, P, then I can calculate it. Okay, and I know that fictitious elements do not exist, so I can put a lot of fictitious elements to make a simple dipole antenna arrangement. Plus, 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 minus, minus, minus. Okay. So we are moving away from physics, coming back to our engineering domain. Make sense? So P is given, and we know that P is related to E theta and E phi. And just to cross verify what we have done makes sense, if we calculate E theta using equations above, if we calculate H phi using equations above, we will get eta, or almost get eta. Okay, so this is a cross verification of our analysis being correct, that if we take a ratio of E theta and H phi, we will get impedance of free space. That is 377. So this equation is telling us another thing, that Ohm's law also exists in free space. Okay. So E theta is equal to eta h. So it's similar to V is equal to IR basically. V is electric field variation, so potential difference is equal to IR. I will produce H. So R is eta here. Okay. And its units are also similar. So eta is in ohms. It's basically resistance R. Okay. So it is kind of combining everything together for us. It's a very, very good thing. And this is the same thing that I have mentioned last time. So in a given area dA, 2 pi r square sine theta d phi d theta is what we are going to get if we want to see how much power we are getting at a given surface. So if we take this integral, of course, I'm not going to ask you this. This maths is out of your scope, but this is for your own information. If we are interested in the surface area, that is what we are interested in. Okay, why we are interested in? Let me explain. Imagine I am building this kind of whole thing for application, say Wi-Fi application. Okay, I have that kind of router. I built an antenna. I put that antenna into that router. Okay, and I'm an engineer. I want to see how much power I need to radiate from there. Okay, so what I need is where exactly a client will receive that energy and how much power that client will receive. Okay, so for example, if there is a requirement for signal to noise ratio by my chip, then I will stand here and I will make a small area. I will say, okay, if the aperture of the client is this much, how much power the client will receive if I radiate another a power P from there. Okay, so that surface area, I will take surface integral of this power equation and I will get a particular value. That is 80 pi square dl over phi I effective. I effective is the effective current that I am going to push there in that router. Okay, so this equation is very useful for me. Similarly, if I want to build a base station antenna and I want to serve entire Belfast, of course, it's not possible using single base station antenna. You will see down the line. But if I want to cover a sector, say for example, from this point till HB building, and I want to build an antenna on top of HB building just to cover this area, then I need to know how much sector it can cover and what kind of power I need to push into my base station antenna so that I will receive a particular power in that given sector, so that your mobile phone antenna can actually receive something and you get your full bar of signals. Okay, so that thing can be manifested easily using this kind of power equation. Okay, it's calculatable. Of course, now we use computers to do this job for us. I will just put this equation in a computer edit program and it will give me exact P value. I don't have to sit down with a calculator to do this job myself. Computers can do this job for us, but it is extremely important to understand what's going on. Make sense? Okay. So there is one last thing about radiation resistance. So whenever we are throwing energy in free space, there is a free space intrinsic impedance. So I want to match my source impedance with that load impedance. And there is a impedance that is in the middle. We call it radiation resistance. Radiation resistance, so R-rad. Okay. So almost it is equal to 80 pi square dl over lambda. Since dl is approaching to 0, our radiation resistance will also be approaching to 0. Okay, because it's a very small number, and very small number squared is even smaller. 0.01 square is 0.000 something. Okay, so it's very small. So dl is what is fictitious, so that's why radiation resistance is also considered fictitious. But in reality, in practical sense, we can calculate it by actually pushing some energy and seeing what is coming back and calculating our radiation resistance from a given antenna. So radiation resistance for each antenna is different and it is very, very subjective to structure of antenna. So if you have mobile phone antenna, it will have different. If you have this Wi-Fi antenna, it will be different. If you have dish, parabolic dish antenna, it will be different. Okay. So anyways, now we have touched our practical scenarios and we have 11:53. Okay. So let's have a quick 5-minute break after your attendance. And for this is for international students, please. It's for that kind of your tier 2 visa thing and or tier 4 visa thing. I don't know exactly what it means. And we will meet again at, wait a second, at 11:59. We will meet again at 11:59. Okay. Yeah. Yeah. You are? Yeah.
Yeah, we told them all. It's good for me. You've already stayed long. I guess it's just.
Okay, let's continue our discussion. So what we have seen is theoretical to practical analysis. Let's look at a simple practical antenna and how it radiates. Okay. So I have done this discussion with you before, that in a simple transmission line or a simple circuit with a positive and negative terminal, electricity do not flow because of electrons leaving batteries and going all the way to a bulb and then coming back. It's not how things work. It's basically electric field trying to change magnetic field at a small area, and then that that electric field changing another variation, producing another variation in electrons or charge density at another area, and then so on. So this is a simple explanation of how antennas radiate. So if you have an alternating voltage source connected to impedance matched dipole antenna, you will have negative current, negative charge on the negative side, positive charge on the positive side, and because of this change in charge, you will have electric field lines. And if those electric field lines are there and you flip the polarity, then there will be another electric field lines, and the other electric field line will have negative direction, and that negative direction will complete the loop, and that completion of loop will produce our electric field completion, and it will leave the antenna body and energy will start flowing through free space. Okay, so this is kind of a simple explanation. I will go a little bit deeper than that just for your own understanding. So okay, I will go with the yellow one. Okay, so let me try to use a bit of color code. Imagine I have an alternating current source connected to a bunch of wires. Okay. Let these bunch of wires have a thickness and has a capacity of having charge density at different areas. So what it means is, let's consider this to be a metal. Metal has free charge carrying electrons. So okay, we can move our charges around. So if I have a positive polarity here, what will happen? There'll be positive charge and there'll be negative charge here. Okay. So electric field lines will flow from positive to from positive to negative, negative to positive. Like this or the other way around. From positive to negative, right? Are you guys hungry? Wake up. Okay. So this will happen, right? Right? Make sense? For the next polarity, what will happen? For the next polarity, what will happen? These charges will move forward. Okay. So what will happen is this whole thing will move one step forward. So we will have positive here, negative here, and we will have our electric field lines from positive to negative here. And then there will be a change of polarity. So positive here, negative here, and lines other way around. Make sense? What will happen next for the next polarity? This whole thing will move here, right? And what will happen for the next polarity? This whole thing will move another step, right? So just consider this to be the new thing and this to be the old one. Okay, so negative, negative, positive, positive. Right? Make sense? Everything clear so far? Now, what will happen if I start twisting this metal like this? And for the next variation, this whole thing will move forward. Consider this new thing to be something like this. Positive, positive, negative, negative. Okay. So what will be the line, the electric field lines? What will be the shape of electric field lines? A bit curved, yes. So like this. Right? And for these, right? What will happen for the next cycle? Now let's make them straight stripes. So this one is negative, this one is positive. So there will be electric field lines from here to here. Is it clear enough? Yeah, clear enough. Right? Right? Now I have stopped building my metal anymore. What will happen next cycle? I have alternating voltage source there, what will happen at the next cycle? Huh? Okay, direction will change, and then I don't have any more metal to handle the next cycle. What will happen? What will happen? But there is already field there. Field is energy. That energy cannot be destroyed. Can transfer, but cannot be destroyed. Energy is there already. So I've already done this action. Electric field lines are there. That is close explanation. But how exactly? So positive and negative need to complete its loop. Okay. So what will happen is I will redraw some of this portion to give of space, a bit of space. So during this cycle, our negative to positive will go something like this. So, and okay. So if I push next cycle, this thing will move forward, and it has to have another opposite structure to complete its loop. So this will move out. So let's consider this to be the next cycle without anything. Okay. Without anything, but it will just stay for half a cycle, and then there will be another next flip, another cycle, and then whole thing will move forward, and it will have a completion of its own. So this will be a complete of loop here, complete of loop here, completion of loop here. Okay, so positive, negative connected to each other to make a full-fledged loop, and this whole loop is itself a complete loop of electric field, and it will move away from this whole thing, this radiating body, and it will go to free space. Make sense? Any questions from this explanation? So this is how a simple dipole is built. A simple dipole is basically an alternating voltage source connected to a transmission line, and that transmission line has an opening, and it has a structure like two strips. Important thing is this needs to be a particular length, L. And for our own understanding, we generally consider this L to be half wavelength, lambda by 2. Because half wavelength is a nice number for us to understand what's going on. If you have half wavelength, it means that at one given frequency, half of this length will be used for positive side, and for the next flip cycle, it will be flipped. So it will produce a wave radiating outside an antenna of a frequency f that has a lambda wavelength. Okay. So given this, we can say that antennas radiate like a simple dipole antenna radiates in a way, what? As given here. Okay, so this is how simple antennas radiate. Okay, simple dipole antenna. Now there are much more deeper understanding of dipole antennas, and some dipole antennas are small in length, so their length approaches towards Hertzian dipole. Hertzian dipole is fictitious, but if we have a super small radiating body, then it is considered close to a simple dipole antenna. Okay, so we can also create a simple electric field based dipole using this kind of phenomena, and we can also have magnetic field in a loop to produce magnetic field. So let me explain what I mean by that. So imagine if I have green one. Okay, I will go back to blue. Okay, so we have seen that a simple current carrying stripe with a positive and negative terminal is a electric dipole. Okay, with this arrangement, we will have current I going up and down and up and down in this stripe. Okay, what does current carrying stripe produce in a loop, right? So it produces a magnetic field like this. B is equal to mu H, right? It produces magnetic field, right? So if I just get rid of this thing and make a simple loop, then this loop will produce a current in the center, right? So it means that I can build a dipole antenna using magnetic field because they are interchangeable, right? So it's possible. Magnetic dipole is also possible. In some applications, we actually build magnetic dipoles. So for example, you have seen those hats. If a hat has a coil like this, then it kind of produces electric field in a way that it produces a magnetic dipole. It just has an opposite polarity, just works in a similar fashion. So these are called loop antennas. So they are also they're also very useful. So some other antenna structures have we can have consist of a transmission line, a simple antenna, a simple transmission line, a dipole antenna, a waveguide connected to a horn antenna, and a simple waveguide with a ground plane that will radiate in a body. Okay, so this is basic understanding about antennas. Now let's look at some definitions that we generally use in antenna theory analysis and designing. Okay, so the first definition is directivity D. Directivity D. Just be considerate that this directivity D is different from electric displacement D that we have seen in Maxwell's equations. Take a note of it. Directivity is different than electric displacement D. Okay, so what is directivity? Directivity is basically, by definition, radiation intensity in a given direction divided by total radiation intensity in all directions. spread across in all directions. Okay, so let me try to explain this and then I will come to this equation. Imagine I have a simple coordinate system and a simple dipole here. Okay, where will it radiate? Everywhere? Will it radiate everywhere? Should, right? So it will radiate here, it will radiate here, 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 right? This is good for some applications, but in some other applications, imagine I want to build an antenna that want to communicate with a satellite. Is this a good antenna for that application? What I need an antenna that radiates in one direction more and basically radiate not at all in other directions. Okay, so what I need is an antenna that is radiating more towards satellite and very less towards other directions. Okay, so this kind of concept is defined by directivity of an antenna. So if an antenna is directive or its directivity is more, it means it is radiating more in one direction compared to all other directions. Okay, so for example, if this antenna is an isotropic, its directivity is 1, then I need a satellite antenna that's directivity is say 20 and all other directions should be 0.2. Okay, it should radiate more 20 times here but very less here in other directions because I'm losing power by throwing it in direction where I don't want it. Okay, so you might have seen this kind of antennas, something like this, parabolic dish antenna or parabolic reflector. Okay, so these are highly directive antennas. Similarly, you have log periodic. And have you ever seen something like this? Yeah, this is a directive antenna. Okay, it throws energy here and captures energy from here more than compared to any other direction. Okay, so directivity is a very useful thing for us. It has a relationship with other useful things as well. So I will come to that. So directivity is basically radiation intensity in a given direction divided by radiation intensity in all different directions. And mathematically speaking, if U is the radiation intensity, then D is equal to 4 pi mu theta and phi. So mu is in spherical coordinate system divided by total transmit power PT by the antenna. And total transmit power can be calculated first by looking at how much voltage I am pushing here and how much current this whole thing is drawing, and P is equal to VI. Or I can take a summation or surface integral of all the power that is radiated by this antenna and divide my 4 pi intensity over this other thing. Okay. So just a few examples. A simple isotropic antenna has directivity of 1. Isotropic antenna is an ideal antenna that radiates in all directions. It's not possible humanly, so it's just like a fictitious thing. It's more related to physics than sorry, to mathematics than to real world. Isotropic antenna has directivity of 1. We have short dipole, a small dipole has directivity of 1.5. We have half wavelength dipole 1.64 and quarter wave dipole over an ideal ground plane. It's also called monopole. You might have seen many monopoles. Have you ever seen a vehicle with this thing? Oh, you cannot see it. Something like this with a long leg connected to it. These sort of vehicles. So these are monopoles. Okay. So similarly, some radio towers are considered monopoles. So if we have a mountain and a long antenna, it's also called monopole. Okay, so have you seen monopole on Davis? Long antenna. Okay. Similarly, we have multiple antenna examples of similar sort. Okay. So antenna power gain. So here's the concept. If I have an ideal antenna, it means it is radiating in all directions. But to generate an ideal antenna is impossible. So directivity is very useful for me to actually define how much antenna is radiating, but practically it do not serve all the purposes. So here's a simple thing. Imagine I have an alternating voltage source connected to an antenna. Okay. Do you think all the power that I throw in to the antenna is going to radiate? It's not possible. It's impossible, right? So what will happen if I put some energy into this antenna structure? Some of the energy will go to waste because of ohmic losses, because of heat dissipation, because of mismatch losses, because of all sort of crazy stuff, right? What will happen? My efficiency will never be 100%. The 100% efficiency is not possible. 100% not possible. So if I have an antenna that is 90% efficient, it's good enough. Even 80% efficient, even 60% efficient, good enough. Okay. From application to application, it's different from different applications, different for different applications. Okay. So, but ideal 100% efficiency is not possible. So, what is a better understanding of this? This particular directivity thing is gain. So, gain has two definitions. So, first definition is maximum power received or radiated from a given antenna divided by maximum power received or radiated from a reference antenna. In our case, reference antenna is an isotropic radiator. Okay, so it is kind of it. That's why the unit of gain is in dBi. dBi means dB is a scale and I is isotropic. So dBi is dB isotropic. So it is kind of a relative term. But more plausible definition of gain is efficiency times directivity. That is mainly used frequently. It is efficiency time directivity. So if I know the directivity of my antenna, the same concept, if I know D, then D is of no use if I am considering ideal conditions. If I multiply it by an efficiency, then this is gain. Eta is efficiency. If efficiency is 90%, then it is 0.9 multiplied by directivity. This gain is more, you can say, realistic compared to directivity term. So why do we need gain? Why are we considering gain? So here is in this chart, you can see, imagine I have a gain at one scale and distance in another scale, and the overall area that antenna is, you can say, providing coverage in is more or less. Okay. So consider this. We have a stick. Okay. So if we want to provide coverage till 20 miles, gain of an antenna is okay to be 3. Okay. It's a low gain antenna. It's providing less area of coverage. Less, you can say, distance, but it is providing more area, more coverage area. So 120 degree. So an example of this antenna is base station antenna. It has 120-degree sector coverage, but the antenna is good enough to only throw energy till 20 miles. Okay. If we want to throw energy at a, you can say, medium level, or say 50 miles, we can use a high gain antenna. Say 9 dBi of antenna can push our energy till 50 miles. But my sector will then be pushed down from 120 to 60 degree. Okay. So more sector, less gain. Small sector, more gain, more distance. And if I want to throw energy till 80 miles, then I need 15 dBi of antenna gain. And my sector will then be 30 degrees, even smaller than that, even shorter sector. Okay. So these antennas are for more directive purposes. So for example, that antenna is a high gain antenna. A high gain antenna means it has more directivity towards one direction. So it will capture a signal from far away distance in that direction and can throw energy in that direction, like more further away. Okay. Similarly, we have much more sophisticated antennas. So for example, radio astronomy antennas have extreme gains. So gains more than 50 dBi. Okay. And they have they have extreme capacity of receiving signal from far away distances. Okay. So that's why gain is an important term and the stick is good. Okay. So this is what I have just mentioned. Gain is efficiency time directivity. So this is another example of why do we really focus on this gain thing. So if we have a 3 dBi of gain and a car with and a simple antenna, then 3 dBi of gain with more coverage is sometimes better than uh, an antenna with extreme coverage, but with less sectoral coverage. Okay, so it's very application specific. It's a complete new field for engineering domain. So there are different antennas for different purposes. So for example, okay, let me ask you a few questions. I haven't asked any question for long. Example of antennas. Any example of antennas? Phone, yes. Any other? Yes. Toy cars. It has a simple communication system. A walkie-talkie, yeah. Radio, yes. Radio is a good example. Radio has also a tuner, so it means that which frequency you want to tune, you can actually tune to that frequency. So it has that voltage source tunable. It's a good thing. Any other examples? Which one? Data. Okay, data has two things. One is data can be from Wi-Fi or from GSM or 3G, 4G. Both have antennas. Both have different antennas. Okay. Any other example? Which one? Microphone. Yes, it has an antenna here. This thing is an antenna. Any other example? TV. That previous slide was a TV antenna. Yeah. We can say there are antennas everywhere. Okay. Just in this room, we have like many antennas. How many antennas do you think we have in single mobile phone or this iPad thingy? How many? R- Wild guess. 6. Very accurate guess. So almost 6. Okay. So Bluetooth, Wi-Fi, GSM or 4G, 5G, LTE, it's kind of a similar thing. And what else? There's PIFA for ah NFC, near field thingy, that card thing. No, I don't call it an antenna, to be honest. It's a near field. It's basically an inductor talking to another inductor. Okay, so it's not antenna. I don't call it antenna. Okay, so which one? GPS. Yes, GPS. I missed GPS. So every phone has a GPS antenna now. Okay, so there's GNSS, there's Galileo and stuff like that. And any example of antennas that are bigger than what we generally use in our day-to-day life? Long ones. Yeah, That's a good example. They're low frequency antennas, but big ones. Okay, huge antennas. Um, we have many space missions. Okay, those space missions will have no sense if they don't have antennas. If they cannot communicate back to Earth, they're useless. Okay, so any satellite that is going out should have an antenna. They generally don't have single antennas; there are multiple antennas. But it's a requirement. So any wireless communication system need antennas, and antennas that's why very useful field of investigation. Okay, so these gains and these terms of are very useful. So about antenna efficiency, it's again it has a mathematical definition as well. A radiation efficiency is equal to R radiation over R radiation plus RL. So that's another definition. Some people use it, some people don't. What we generally like to do is to actually build antenna and see how much input resistance it is giving us, and then trying to match it with the load. Okay, trying to match it with the source. Okay, so it's very antenna specific. So some of these definitions are very antenna specific. Okay, so let's look at another very useful thing that is called radiation patterns. And if we just look at a simple Hertzian dipole, and imagine this Hertzian dipole is fed by simple current I, and I is I naught E j omega t. Um, what is E j omega t equals to? How many of you have seen Euler's identity? Euler's identity. You know about Euler's identity? Okay. So what is it exactly? E j omega t would be equal to E j omega t would be equal to what? Cos, sine, something? Cos omega t minus plus j sine omega t by 2 or something like that. Right? Have you seen this before? Okay. It's not accurate enough, but just look at what if this plus or minus if this. So what it means is it's a sinusoidal function. If I'm just considering the positive side or the real side, then it's is e j omega t is basically a sinusoidal function. Okay, so if my I is a sinusoidal function, then my E theta will be 60 pi I dl sine theta over lambda r E minus j k r. K is wave number. Okay, so for now we have seen wave number. We know all these definitions. So if I put this simple antenna at the center of Cartesian coordinate system, sorry, spherical coordinate system, then and if I plot my electric field in theta, then it will look something like this, a donut shape. Okay, so it's just a polar plot of my field that is getting radiated by a simple Hertzian dipole. Okay, if I take a cut in this direction, so this blue axis and red axis, and if I plot it on a screen, then it will look something like infinity shape. Okay, what does this infinity shape means? This infinity shape means it has maximum directivity along these two directions and no directivity along these axes. So I'm just looking at this green curve. So it has maximum directivity in this direction and this direction, and basically no directivity along these directions. So a simple dipole antenna, simple dipole, imagine a dipole in my hand. Antenna will radiate in this direction all around, but it will not radiate in these two directions because current is moving here. Okay, so if I look from the top, the current is just changing here, but it's not changing at all in this direction. Okay, so that's why there will be no radiation, but there will be radiation here. Okay, so that's why this is a very basic or fundamental radiation pattern of an antenna or a Hertzian dipole. For proof of this equation, you can actually look at this book, Foundation of Antenna Theory and Design, by Professor Vincent Fusco, who was a professor here in Queens. And so Let's go again towards some fictitious definition, and then we can build our argument based on those definitions. So a simple Hertzian dipole has its coverage area defined by half power beamwidth. So half power beamwidth is defined something like this. Imagine I have an ideal antenna. It is radiating equally in all directions. Now I replace that ideal antenna with a directive antenna which has more radiation in one direction and less in all other direction. Do you think it is possible to make an antenna that radiates only in one direction? It is not possible. Okay, practically it's impossible to make such an antenna. It's not real. So what happens is antennas radiate more in one direction, but they also leak energy in other directions. Okay, so half power beamwidth is a very good way of identifying where does the antenna energy, radiating energy, is concentrated. So half power beamwidth is something like the beam in which more than half of the power that is radiated resides is half power beamwidth. Okay, for a simple dipole antenna, this half power beamwidth is almost 90 degree. So what it means is, if I have a dipole antenna here in my hand, like this, then it will radiate 90 degree. Its sector will be 90 degree all around, like this. Okay. So half power will be residing in this 90 degree area, and all other energy will be in other directions. Okay. So this is fictitious definition. And if we look at the radiation pattern of a dipole antenna, as I have mentioned before, on the if Hertzian dipole is like this here, then it will radiate like this. It will have maximum radiation along y-axis and no radiation along z-axis. And if we look at the dipole antenna from top side, then it will have equal radiation in all directions, looking like this, right? Okay. A few examples. You might have seen these antennas before. So if the antenna length is lambda by 2, its radiation pattern will look something like this. And it's a practical antenna. It's actually used in day-to-day life. Its half power beam width is 78 degrees, approximately 78 degrees. Okay, so it means that in 78-degree beam width, it will radiate like maximally in this 78-degree beam width. So that's why walkie-talkies they will work if you are putting them like this. But if you are putting like this towards who you want to speak, they will receive basically nothing. Sometime from multipaths they will receive something, but basically in an ideal world, nothing. So a lambda wave, a full wavelength dipole has smaller half power beam width, and I think it was 3 lambda by 2, and it has 19 degree of beam width, but it has nulls. So it means this is not a very good design to use in a communication system. These designs are used for like multicast and broadcast systems, but not for our day-to-day life. So, okay. Where are we? Okay. So just a few more concepts, and then we will continue our discussion in the next class. Okay. Let me give you another important piece of information that is very, very useful. Let's go back to this yellow thing. Okay, now previously we have seen more theoretical power-based definitions. Now let's look at an actual example. Imagine I want to communicate with a satellite far, far away. Okay, imagine I am on land. This is Earth. I have a directive antenna, and I'm trying to communicate with a satellite here. Okay. So here's the thing. The power that I need is the power that I will capture at an aperture of the antenna that is placed on my satellite. Okay, let's consider that to be a simple dish antenna or parabolic reflector antenna. Okay, so if I look at the front side of this dish, it will look something like this, right? There is another thing that is called distance from the transmitter to receiver. Okay, let's call it distance d. Okay, the transmit antenna will also have a gain. Okay, but whenever it will radiate energy, it will radiate in all directions, but more in one directions. Okay, so this radiation will move in all directions. Okay, so what I am most interested in is how much power I am pushing into the antenna, or called PT, transmit power. How much is the gain of the transmit antenna, GT? What is the gain of my receiver antenna, GR? Okay, and the total power that is being radiated and that is spread across in all different directions. So, okay, so there will be some energy going here, some energy going here, but I am only interested in this particular small little area, this one. Okay, if I want to mathematically write this whole thing, this whole example, then I use free space equation that will give me exactly how much power receive I will get, and it depends upon the aperture area of the received antenna. Okay, so the equation is something like PR so the equation is something like PR, or received power, or let's look one step above. The PR is total intensity of the transmit antenna multiplied by the aperture of the received antenna. Okay, so total intensity of the transmit antenna and aperture of received antenna. Okay, and if I do some small little mathematics, then I can end up with this very useful, very extremely useful equation that's called Friis free space equation. And this equation is saying something like this: received power PR in that small aperture area is equal to PT, transmit power, PT, GT, gain of transmit antenna, GR, gain of receive antenna, multiplied by lambda over 4 pi R, and R is the distance from transmitter to receiver, squared. Okay, so if I am sitting at a satellite and I want to calculate how much power I will receive, what information I need? I need how much information was transmitted, PD. What is the gain of the transmit antenna, GT? What is the gain of my receiver antenna that is actually on the satellite? What is the distance R from the ground station to the satellite? And lambda is the wavelength of frequency of operation. Right? This equation makes sense? This equation is called Friis free space transmission equation, and it's extremely useful. What it kind of gives us is, what it explains is, we have very less control on some of the things and we have very high control on some other things. The less control is on R, the transmit, the distance between receiver and transmitter. If it is huge, it is huge. We can do nothing about it. Okay. But what we can control is gain of transmit antenna and gain of receiver antenna. Okay. So gain of transmit antenna, we can use a high gain antenna for transmission. We can use a high gain antenna for the reception. We can push more energy in the transmitter, so PT. So we can push more energy here. We can push more energy here, PT. to the transmit antenna. Okay, so that's why your mobile phone battery actually defines how much maximum PT you can get. Shape of your mobile phone antenna defines how much GT you will get. The PR at the receiver or at the base station is going to determine how much power is getting received. So a receiver sensitivity, that is something not linked with your with your module, defines how little power a receiver can actually make sense out of. Okay, so that is a job for a base station. So that's why a lot of sophistication and a lot of engineering innovation is required in this particular designing principle, because this received power actually depends upon our transmit power, how much maximum power we can transmit, how much gain we can get at a given location or at a given space, and how much gain we can have for the receiver side. So this is a very, very important equation. Okay. So any questions? What we have covered so far? No? Okay. So I think we should stop here. Otherwise, you you will be your brain will freeze. So the received energy PR has, we have multiple different methods of producing high gain antennas. We can use lenses, we can use multiple antennas that are phase aligned, we can use mirrors or reflectors and these kind of things. But these are you can say example classification of antennas that are not directly linked with it. Anyways, let's meet on Monday in our lab. You know the location of your lab? You don't know the location of your lab? Look at your Canvas announcements. Okay, so you will get your lab schedule there, and let's meet on Monday. Thank you very much. There was attendance sheet going around. Yeah. Anyone who haven't marked attendance, please do so now. Thank you very much. Yeah.